Thanks so much for joining us today. I've had a lot of fun putting this talk together for you. I'm Kate Pilkington. I'm based in Australia. I'm the Technical Applications Specialist for Cytek Biosciences. And during this presentation today, as I said, if you have questions, tuck them in the window. We don't have time to stop during the flow, but we will take care of it at the end. And before Lara presents to us later about her panel design and her research and how she's applied those together, I'm going to give you a very high-level overview of panel design concepts. So before we speak about those panel design concepts, and so that you don't have my little bobblehead going around, I'm going to kill my camera for the speech. Before we speak about panel design concepts, let me talk to you about how a spectral cytometer is providing data output that's different in the way that a conventional cytometer is working. So using the example of PE, this graphic is illustrating the emission profile of PE. And on a conventional cytometer, the fluorescence emitted from PE is utilized in just one bandpass filter. And in this example, it's bandpass filter 2. However, any light in the neighboring bandpass filters need to be compensated out, and all other portions of the spectrum are completely disregarded. In comparison, when we look on Aurora, if we look at our PE, we capture light from the entire emission spectrum, and we exclude only those portions of the spectrum which coincide with laser excitation frequencies. And in this way, we capture so much more information from every single fluorochrome on every single particle. But not only that, we also capture that information from every laser present on the Aurora as well. For every laser on the Aurora, there is a matching module of light detectors that collect light from just above the laser excitation wavelength all the way through to 830 nanometers. For example, the blue laser collects emitted light from 500 nanometers to 830 nanometers, while the UV module collects light from 365 nanometers to 830 nanometers, and so on for each laser on the system. In this way, we not only collect emission from the entire spectrum from the primary excitation of a given fluor, but we collect the emission spectrum of that fluor from every laser present. This single laser blue spectral plot most closely resembles the PE emission profile that I showed you on the previous slide. So with the box channels outlining the portion of the spectrum that's characterized by a conventional cytometer. Observe that when we characterize the PE emission from every laser on the system, we gain a lot more information about how PE is emitting fluorescence, and correspondingly, how this fluorochrome is likely to contribute spread into other fluors in a multicolor assay. This profile is a unique signature or the fingerprint of PE, and armed with this information, we are no longer limited to using just one fluor in one bandpass detector. We can use highly overlapping dyes and still resolve our populations of interest. For example, take PE and the new Cytek C fluor BYG584. These fluors have highly overlapping spectra, and if assessed on a conventional cytometer, would be incompatible in a multicolor panel. But when we look at their spectral fingerprints, we find that there are a number of areas in which they are different. And this difference enables us to spectrally unmix them and use them in the same multicolor panel, and with very careful panel design considerations, even use them on co-express markers. Spectral unmixing, much like compensation, involves informing the cytometer about the fluorochromes present in the assay with the use of single-stained reference controls. And then the ordinary least squares algorithm is used to calculate the contribution of each known fluorochrome spectra to the total collected emission signal. Observe this three-color mixed example. When we extract or deconvolute each component until nothing is left, we are calculating and solving for the minimum. And the eagle-eyed among you may have noticed 4 lines in this three-color animation, which leads me to one of my very favorite topics, cellular autofluorescence. In the same way that we characterize and assess the contribution of each fluorochrome in the panel, we can also characterize and not just assess, but extract the autofluorescence contributed from cells in an assay. Observing the 2 signatures on the left, we can see that the unstained HeLa cells have a very high autofluorescent profile. And when we have transduced them with M-Cherry reporter, the M-Cherry signature is really weakly positive and it's quite subtle. So what does this mean in the way that we visualize the data? When we examine the unstained cells and plot side scatter on the x-axis versus M-Cherry on the y-axis, we observe a very widely spread negative population with respect to that M-Cherry. If we do not extract autofluorescence, we see a minor shift of positivity from the M cherry, which can prove quite challenging when we wish to assess the efficiency of the transduction. However, when we turn on autofluorescence extraction, we are able to remove the contribution of the autofluorescence from the M cherry and observe a much cleaner shift. Different cell types and different treatment and different staining conditions can alter the autofluorescent properties of our cells. Therefore, it is really important that we provide appropriate unstained controls to accurately assess the contribution of autofluorescence in our assays. So now that you understand how Aurora works and how we can leverage the unique signatures we observe for our analysis, we are armed with even more information that's going to help us in our panel design as well. The foundation of every single panel design needs to revolve around your experimental question. When you know the desired outcome, all that remains is a process that is driven by a number of separate factors to help you find that answer. Now let us start from the beginning. For every panel design I wish to make, my starting point is always the biology of the sample. We need to understand the antigen expression profile, and in order for us to do this, we need two main pieces of information. We need to understand the classification of each antigen. This classification system was described by Yolanda Mankey and Mario Roeder in 2007 and involves assigning antigens to three main classes: primary, secondary, and tertiary. Primary antigens are those with a high density and exhibit an on or off expression style, for example, CD3, CD19, or CD14, whereas secondary antigens are those with an intermediate density and often exhibit continuous expression patterns, for example, CCR7, HLA-DR, or CD38. Our tertiary antigens are those with low density or unknown expression, and this is often the category to which you're going to assign those antigens in your panel which are most closely associated with your experimental question. But antigen expression is far more complicated than simple classification. It is also vital that we understand the co-expression patterns of each antigen in the assay. Those antigens that are mutually exclusive and those which are co-expressed will have varying impacts on our panel design. So use the literature available to help you establish your understanding of the co-expression patterns of as many antigens in your panel as you can. And when we have this information in front of us, we're then ready to move on to the next step, which is our fluorochrome selection. When we're considering the best fluorochrome to assign to each antigen, we need to take into account three factors: fluorochrome uniqueness, fluorochrome brightness, and cross-stain index, which is a measure of the spread contribution of one fluorochrome into other fluorochromes. So we have lots of tools here to help you with this stage of panel design. Let me walk you through them. Starting with fluorochrome uniqueness, I never design a panel without consulting our Cytek Spectrum viewer. The viewer can be adjusted to match your Aurora or Northern Lights configuration and help you to understand how each fluorochrome is characterized spectrally. The Spectrum viewer also has a similarity index tool built into it. The similarity index is a measure of the uniqueness between two fluors. An index of 1 means that the spectra match exactly, and an index of 0 means that the spectra are completely different. For panel design, the more unique the set of dyes are, the easier that they are to use together and the less spillover you will observe. In the first example on this slide, we see Percy-P Cy 5.5 and Percy-P eFluor 710, and these two dyes are highly overlapping. The similarity between these two dyes has a similarity index of 0.9. In our second example, we observe BUV 395 and APC. Note that in any channel where the BUV 395 is emitting light, APC is not, and vice versa. These two dyes have a similarity index of absolutely 0. So if you're looking for inspiration of unique dyes that can potentially be used together, we recently published an optimized multicolor immunophenotyping panel demonstrating the first 40-color fluorescence immunophenotyping. If you look closely at the panel design, you're going to find that dyes that are highly overlapping, such as BV421, Superbright 436, and eFluor 450, are assigned to antigens that are mutually exclusive in their cellular expression. In a panel of this complexity, it is essential to minimize the spread from highly overlapping dyes by assigning the fluors to non-co-expressed antigens. So this is really a wonderful time in which to be designing new panels of high complexity with a plethora of new dyes on the market to help you move beyond your classical fluorochrome assignments and add in more unique fluors. In our 40 color panel design, there are 7 new dyes that were essential in achieving this dimensionality. Here at Cytek, we have just released 3 new fluors, one of which is in this panel, C-Fluor BYG584. And as we have discussed, this is unique from PE and they can be used together. So it's a great addition for your next high dimensional panel. On top of their already extensive fluorochrome palette, Biolegends now have their spark dyes, their new fire tandems, as well as Caravia Blue. 2 of the spark dyes and 2 of the fire tandems have been incorporated into our 40 color panel as well. And if you look here, you'll notice that the spark blue can be used along with BB515 and FITSI, giving us 3 in a traditional space where normally 1 fluorochrome can be used. As well as this, there are new PE Alexa tandems that slot into some convenient caps in the spectrum as well, also with some unique signatures. So the next characteristic that we need to understand about fluorochromes is their inherent brightness. We assess brightness by calculating the stain index of each fluorochrome when conjugated to CD4. In this way, the changes in brightness are attributable to the fluorochrome and not antigen density. Each of our fluorochrome guides includes a stain index of fluorochromes to help you get along with this process. Our fluorochrome guides can be downloaded from our website and help you out. In this chart, we've listed these fluors in order from dimmest on the left to brightest on the right. And when deciding which fluor is best to assign to each antigen, it is ideal to assign the antigens with highest antigen expression to dimmer fluors and those antigens with low expression to brighter fluors. But while fluorochrome brightness will be an important factor in your assignment in a multicolor panel, it is not the most important consideration. Arguably, the property of a fluorochrome that will have the biggest impact on your panel design is how much spread it contributes to other fluors in the assay. Quality panel design is a balancing act aimed at managing fluorochrome spread. As well as the spectral viewer and the brightness index tools I just mentioned, you can also find a cross-stain index, which is what I like to call CSI Cytek in our fluorochrome guides on the website. So to read these tables, you're going to look spread from the fluor in the row impacts the resolution of the fluorochrome in the column. So red means the fluor in the row has significant spread into the dye in the column, and areas in the bright pink and red indicate pairs for which more attention to panel design is needed. For example, when we look at the spread of APC into BUV395, 0% spread is observed and all our populations are well resolved. Conversely, when we look at the spread of FITSI into Spark Blue 550, 76% spread is observed. And as a result, that negative population is significantly spread. And in order for us to manage this spread, these 2 fluors have been assigned to mutually exclusive antigens whose expression patterns are well resolved from the negative. Up to this point, everything that we've just discussed has been conducted in silico. Now it's time for us to step into the lab and begin testing our panel. But we don't just throw our antibodies into a tube and have a look. I like to think of quality panel design like building a skyscraper. The top of the skyscraper, it's your beautiful panel, but no skyscraper is built from the top down. In order for us to achieve these lofty heights, we need robust and quality foundations. In terms of our panel, the foundations are our controls. So what are the properties of a good single-stained reference control that will allow us to succeed? First, we need our positive and our negative particles to be clearly separated. In order to achieve the best separation, it is essential to titrate your reagents to obtain optimal staining. Second, we need to ensure that our negative and positive particles have identical autofluorescence characteristics. For example, you cannot use unstained cells as the negative particle for positively stained beads, as the negative population will look significantly different between these 2 particle types. The same is said between unstimulated and stimulated cells. Each different process that you subject your cells to may alter their autofluorescent properties, and therefore it's important to consider how best to obtain negative particles to match your positive stained particles. Third, the easiest one to achieve in many cases is we need sufficient events for both data points. And finally, the fluorescence spectrum of the positive control needs to be identical to the one in the multicolor sample. Antibody capture beads need very careful consideration in this respect, as some fluors will undergo a slight change in emission when bound to beads compared to binding to cells, and Lara is going to speak a little more to this in detail in her portion of the presentation. How do we know if our controls are optimal? In order to assess the unmixing accuracy, which is driven by the input we provided in the form of those single-stained reference controls, we look at permutations of each fluorochrome versus every other fluorochrome in the assay. When observing these plots, we wish to see nice straight lines and orthogonal staining, no curved size-like populations that curve above or below the negative population fluorescence. After checking the permutations from our single-stain reference controls, it's always a good idea to observe our multicolor sample and make sure we are seeing the same orthogonal staining patterns, which we have in this nice data set here. And now it is finally time to assess the performance of the staining of your multicolor panel. This is the tip of your skyscraper, so don't be tempted to jump to this phase without taking due consideration of each of the earlier stages of your panel design. In order for us to determine if our panel allows us to observe the populations we wish to characterize, it is absolutely critical for us to compare our single stain cells with our multicolor stain. The purpose of the single stain cells can be twofold in your assay development. One, not only can they be used as a single stain reference control, but they can be used at the point of evaluation to allow you to assess antibody performance, titer, and staining conditions. And they also enable you to assess the quality of your panel design. By observing fluorochrome X in the single stained tube and the same fluor in the multicolored tube, when we compare these two, we are looking to see if we can maintain population resolution when the fluor is in the cocktail compared to when it is singly stained. And taking the time to compare each marker in a single stained tube against the multicolored tube is the foundation for panel optimization. So let's look at some real data on the next slide. Along the top row, we have our single-stained CD45 RA BUV395 and CCR7 BV421. Along the bottom row, we observe the same fluors in the multicolor sample. When we are assessing panel performance, we need to ensure that our population resolution is still achievable. In the case of CD45 RA BUV395, the single stain and the multicolor demonstrate a very similar degree of spread of the negative, and we are happy with this resolution. In the case of CCR7 BV421, we are observing a little bit more spread of the negative. However, our population is still well resolved. If at any point the spread of the negative prevents you from observing the populations you wish to assess, at this point you need to readdress the panel design, and that could potentially be optimizing by an adjustment to antibody titration, or may require reassignment of that antigen or other antigens that are contributing spread into that fluor to a different color. Then once you're happy with the performance of your single stained and multicolor tube, now you go and get to the fun part, where you can draw up your beautiful gating strategy and check to see if you can observe the populations of interest in your experimental question. It's so tempting to skip to this part right at the start, but if you do, you're going to make your life a little harder. Always go through methodically. So to briefly recap, the segment in blue is all in silico, and the segment in red is what you're going to do in the lab. However, you may find that it is necessary to loop back from panel evaluation into panel design several times in order to get the very best panel with the highest quality data. So now you're keen to start on your own panel design. What options are available to you? Well, there are several ways for you to approach panel design. You can start from scratch and build your own panel. And don't forget all those resources that I've mentioned, which are available to you. Alternatively, you can use an optimized panel, and there are lots of pre-optimized panels that have been published. We have several at Cytek, and there are lots already published in the form of OMIPs. And you may find that the antigens that you're interested in are already in use in another panel. So check out the list of OMIPs to see if there's already one that can get you up and running as quickly as possible. And if you find one that is close to what you need, but not quite the same, then you can go ahead and use it as a starting point and make adjustments and then optimize that to your needs. And to accompany that, let me just add that myself and my fellow TIS at Cytek all around the world are here to help you. We can offer you additional training as well as assistance with panel design feedback, and can even help with your data analysis and troubleshooting. We also have an Aurora user community forum where you can connect with others for advice and help. And finally, don't forget that the internet has a wealth of information. We have many written resources and video tutorials to help you, and there are other sites out there that do the same. So they should help you get going on your spectral cytometry journey. And thank you very much for joining us today. Before I introduce Lara, does anybody have any questions?
Would you like to answer, does the spread comparison, is it only applicable in spectral flow versus traditional flow?
So the spread matrix that we've generated is only applicable to data generated on our spectral cytometer. The spread matrix is going to be different to what you would see on a conventional cytometer. And in fact, because of the way that we are using unique signatures to tease apart the signal, we have more pieces of information for every fluorochrome. We therefore get more accuracy in the separation. You'll find that there's less spread when you use a conventional, when you use a spectral cytometer compared to a conventional cytometer. Let me introduce you to Lara. Lara Ferrer is based at the Malaghan Institute in New Zealand, lucky her. Lara completed her PhD about magnetic resonance imaging for glioblastoma tumors at, do you know what? I'm not going to go with the Spanish version. I'm going to go with the English version at the Autonomous University of Barcelona. She then migrated south for a 2-year postdoc in Malaghan Institute with the Cancer Immunotherapy Group led by Professor Ian Hermans. About a year ago, she joined the Hugh Green Cytometry Centre as a high-dimensional flow cytometry specialist, where she has become their resident expert for supporting Aurora users and so much more. I've had the opportunity to work with Lara many times over the last year, and it gives me great pleasure to introduce her to speak to you about her panel design experiences. Thank you, Lara.
Okay, hello everyone. Let me get my presentation ready. So, hi everyone, and thanks Kate for your awesome introduction. Today I would like to show you as 2 case studies 2 of the projects that involve a spectral flow cytometry and that we have been working on in Malaghan Institute in New Zealand. As in Malaghan Institute we were early adopters of the Aurora, we thought it would be interesting to confirm the potential of this spectral flow cytometer, and that a good way to do it was to compare its performance with the gold standard technology at that time, that was the CyTOF or mass cytometry technology. So for the first case study, we aimed to determine if the Aurora could achieve similar outputs than with CyTOF. And also, we were highly interested in testing if the high-dimensional algorithms that had primarily been used for CyTOF could also be successfully applied to a spectral flow cytometry data. First of all, a brief overview of what mass cytometry is. For mass cytometry, antibodies are conjugated with metal tags to be able to label cells. Also, more than 50 parameters can be analyzed at single cell level, and low spectral overlap. The panel design is easy, and there's no autofluorescence background. However, mass cytometry is a slower technology than flow cytometry, and the speed can go up to 2,000 events per second. It will depend on the tissues you are working on, and usually it will be required the use of pre-sorted samples. In the case of mass cytometry, we lose the site scatter and forward scatter parameters of the cells. And also, as the staining protocol involves lots of washing steps, the 40% of the cells get lost during the staining protocol. Regarding a spectral flow cytometry, Kate has already explained it very well, but I'll give you also a very brief introduction in order to directly compare it with mass cytometry description. So antibodies are conjugated with fluorophores, and in contrast to conventional flow cytometry, a spectral flow cytometry distinguishes the full emission spectrum of each fluorophore rather than identifying only the peak of the emission. With last Cytek publication, they could run 40 parameters at the same time, and if the panel has been well designed and optimized, there's a minimal need for manual compensation. However, as more markers you want to put in your panel, the panel design process becomes more complex. Also, autofluorescence can be considered as one more parameter and can be extracted, as Kate has shown. And the acquisition is much faster than for Cytof. It can go to up to 35,000 events per second for the 3-laser Aurora. In the case of spectral flow cytometry, there's a minimal cell loss during the staining protocol. So how did we design our experiment? For our experiment, we used spleens from C57 mice, and half of the spleen was stained with a 37-color mass cytometry panel and analyzed in Cytof, while the other half of the spleen was stained with a 22 spectral flow cytometry panel and analyzed in the 3-laser Aurora. Importantly, 20 of the antibodies that were used for both technologies were against the same markers and the same clones, what will allow us, after obtaining data, a more reliable comparison between both technologies. When analyzing the data with expert gating, we were surprised of how similar our plots look like when comparing technologies, and also that we could find all our populations of interest in each dataset. To quantify these similarities, we gate on our cells of interest to obtain the frequencies, and we obtain a concordance correlation coefficient of 0.99, where we correlate the frequencies of each cell type in the same sample for the Aurora and for the Cytof. We also made sure that there were no significant differences when comparing the average of each cell type frequency obtained in each instrument. When comparing our data with high-dimensional algorithms, we decided to first use UMAP. UMAP is a dimensionality reduction algorithm that will allow us to visualize the data in 2 dimensions. We needed to run 2 different analyses because the parameters from Cytof and the Aurora were too different, but despite this fact, we were quite surprised to see that our UMAP maps were looking very similar, and that we could identify the same populations in both datasets. We could also identify some differences. So, for example, XCR1 positive events are defined better in the data collected from Aurora, but overall, the analysis looked very comparable. We validated the results by running also t-SNE, that is another dimensionality reduction algorithm, and we found very similar results to the ones obtained with UMAP. Next, we also tested FlowSum. FlowSum is a clustering technique that will group similar cells into clusters. And we also found that both technology analyses look very similar. From these results, we can conclude that data analysis algorithms that were first used for Cytof can successfully be applied for a spectral flow cytometry data. But we will need to ensure a good panel design and that the panel has been well optimized and that there are no compensation issues in our data. The decision between using one technology or the other one will depend on the goal of the project you are working with, or also it will depend on which technology is more accessible for you at the moment. A spectral flow cytometry is preferable for rare populations analysis as it is faster and it allows you to collect easily more events. While if you want to design a very big panel with highly co-expressed markers, maybe Cytof will be the best approach. So based on these criteria, we decided to use a spectral flow cytometry for our second case study. That is about analyzing immune cells of helminth-infected intestines. It is already well known that there are different waves of immune responses against parasites, but a multidimensional kinetic assessment of the infected intestine is still missing. The approach that we follow was to obtain gut helminth-infected single cells from different time points. So we collected samples, gut samples from day 0, when mice were not infected, so naive mice. Also, we collected samples from day 7, that is when the infective larvae undergo larval development in the muscularis externum. Also, we collected samples at day 14, that is when the adult worms are in the lumen and when the peak of acute immunity is usually studied. And as last point, we collected samples at day 28, that is when the infection has become chronic. As helminth infections are strongly linked to chronic impairments that affect, for example, nutrition availability or changes in the microbiota, also modulation of local and systemic immunity, we thought that an optimized digestion protocol was needed to further investigate the infected intestinal tissue. That is why the first goal of this project was to establish a robust digestion protocol for helminth-infected intestines. Next goal was to design a spectral flow cytometry panel with up to 23 colors to simultaneously characterize innate and adaptive components of the type 2 immune response. And the last goal was to investigate our data with high-dimensional data analysis tools. Intestines are very tricky tissue to work with, as there is lots of debris and dead cells. While a standard protocol works well with naive guts, C. live cells, and CD45 positive cells, when using the same protocol for day 14 infected mice, no live or CD45 positive can be obtained. These impossible digest conditions have been linked to increase of the mucus production, immune cell infiltration, and tissue remodeling at day 14 after infection. So, given this condition, there's a need for optimizing a protocol to be able to get single cells out of day 14 infected cats. To optimize the digestion protocol, we use a systemic approach. In the first graph, we are showing the number of viable cells obtained per each iteration of the protocol. Digestion number 1 is the standard protocol, and with this one, we obtain around 5 million live cells out from the naive gut. But when used with the day 14 infected gut, no cells could be obtained, no live cells. After testing some variations in the protocol, the digestion that worked well for day 14 infected guts was number 13. And the same digestion also worked well with naive guts. So finally, we found a digestion that will allow us to obtain live and CD45 cells out of day 14 infected mice. At this point, next goal was to design and optimize a high-quality panel that would be used to assess the immune cells playing a role during helminth infection. I'll use this figure of a paper that we published about panel design that will help me explain the steps that we follow. First, determine the experimental question. In our case, the experimental question was, which immune cells are playing a role during helminth infection? Next step was to know the biology of the tissue or cells of interest, which markers to use, and if they were highly expressed or lowly expressed. Third, we needed to know the instrument configuration, and in our case, we were using the 3-laser Aurora. And also, we needed to know the different spectral signatures. Next step is to assign fluorophores to each marker, taking into account the previous information of the marker expression profiles, plus the spread matrix and the fluorophore brightness, as Kate has explained before. Next step that is highly recommended is to theoretically QC our panel design. To QC the theoretical panel design, this consists of making sure that our design panel is the one that we think is the closest one to the one that will work very good in the reality. At this point, as Kate was saying, we can use the spectral viewer to make sure that our fluorophore choices have unique spectral signatures and that they are well spread across the whole emission range. Also, we can have a look at the similarity indexes to see how similar our fluoros are, and also at the complexity index. The complexity index is an overall measure of uniqueness of all dyes in a full spectrum cytometry panel. In our case, we had a complexity index of 13, and this was a reasonable number for a 23-color panel for the 3-laser Aurora. A 13 complexity index would be a very high complexity index, for example, for a 4-color panel. Also, in order to theoretically validate the panel before proceeding to the practical testing, we suggest reviewing the panel on a marker by marker and cell by cell basis by asking the following questions. The first question is, are fluorophores that induce high amounts of spread allocated to non-co-expressed markers? If yes, cool, we can go to next question. Next question is, do the readout or tertiary markers receive a minimal amount of spread from the other fluorophores? If yes, perfect, we can go to next question. Are fluorophore brightness and antigen expression levels well matched? So are we pairing highly expressed markers with dim fluorophores and lowly expressed markers with bright fluorophores? If yes, we are ready to go to the machine. If no, so in case we find potential issues, markers that are available with multiple fluorophores can be swapped out to see if spillover can be reduced. If yes, we are ready to go to panel optimization at the cytometer. In our case, for our panel optimization, we had to run 11 experiments before we were satisfied with our panel. Today, I won't guide you through these 11 experiments, so I'll only show you some tricks or things that we learn along the way that can be useful when optimizing a high-dimensional immunophenotyping panel. Titrations are extremely important. First, to reduce the non-specific binding, but also to get the best resolution possible, or to make sure that the positive population is a true positive and it's not a spread of the negative population. In our case, some markers were titrated in the spleen, but some other markers weren't expressed in the spleen and had to be titrated in gut, or even they had to be titrated in infected gut. I'm showing here one example of CD11C that could be titrated in the spleen, while GAT3 had to be titrated in gut. I'll show here another example. This is CD11B per CP Sci 5.5 that was titrated in the spleen, and the 1,900 dilution was the optimal one. But when used in the gut, 1,900 was not enough to separate all positive from negatives. So when testing 1,300 dilution, we confirm that the dilution used for the spleen couldn't be used for gut samples and that we needed a higher dilution. So if possible, it's recommended to titrate your antibodies in the tissue of interest. If not, a special attention should be paid to make sure that we are not missing positive events. A must when optimizing your panel is to QC your controls. This means making sure that the spectral pattern of your controls is the expected one and that there is no contamination from other fluorophores. Kate has also already explained to us what a good control is. She has said that it has to be as bright or brighter than our full stain, it has to have enough positive and negative events, and the spectral signature has to match the full stain in order to avoid unmixing issues. Ideally, we would prefer to use cells as single stains because the spectral pattern will be completely matching the pattern of the full stain. But that is not always possible due to restrictions in tissue availability or because the antigen of interest is rare. That is why single stain beads and cells should be compared, as we will need to decide which one to use in order to obtain good mixing accuracy. In this example I'm showing, we were comparing beads and cells from the spleen and cells from gut. And as we can see, there's a small difference in the first part of the spectra regarding the beads compared to cells. So for this example, we will need to use either spleen cells or gut cells for our unmixing. Given the difficulty that we had of working with gut tissue, we would have loved to use beads for all our controls, but some bead controls did not unmix well in our panel. So the approach we follow was the following one. First question, can we use beads? Do the fluor on beads have the same spectra as in gut cells, and are they equally bright or brighter? If yes, Perfect. For this control, we were able to use beads. If no, can we use splint cells? Do the fluor on splint cells have the same spectra as in gut cells, and are they equally bright or brighter? If yes, for this control, we would use splint cells as controls. If no, we would need to use cells from gut. I would like to say that in our panel, we only end up using 2 controls from gut. How to deal with autofluorescence is something that has to be considered. In very highly autofluorescent tissues, it is even recommended to first run your unstain sample and after design your panel considering this autofluorescence signature. To optimize our panel, we tested how the autofluorescence extraction affected our panel. And we found an increase of resolution of some of our markers. Here I'm showing Ly6C BB570 as an example. In blue, the positive population that doesn't change after autofluorescence extraction, while in red, there's a huge shift of the negative population after autofluorescence extraction, increasing the resolution of the Ly6C marker. By testing both iterations, we decided to use autofluorescence extraction for our immunophenotyping panel in gut. Another important step was to validate that the digestion was not damaging our epitopes for the markers of interest. With this idea in mind, we compare non-digested splints with digested splints following the gut protocol, and we found that only 2 markers were significantly affected by the digestion. When differences are found, you need to decide if this won't compromise your results. That is probably the case for CD127, and as there is still a good separation between negative and positive. Or if you will need to change the clone to see if results can be improved. Intracellular staining needs also some considerations. First, fluorophores can become dimmer after intracellular staining, so when designing our panel, we needed to allocate bright fluorophores to intracellular markers if possible. Also, we would need to FC block again our cells after fixed perma steps to avoid inspecific binding of our intracellular markers this time. And we would need to identify the fixed perm buffer that suits better our needs, depending on if we are interested in transcription factors, cytokines, or intracellular proteins. In our panel, we had 4 transcription factors and Ki67, that is a proliferation marker. And we compare 4 different kits, but I'm showing only the results for 2 of them. And as you can see, all the markers perform better with the kit number 1 compared to kit number 2. See, for example, Ki67, where 27.3% of the events were positive for kit number 1, while only a 1.8% for kit number 2 had positive events for Ki67. Similar results were obtained for GATA3, but also for the other markers. So therefore, for our panel, we decided to use kit number 1 for future experiments. When optimizing a panel that has lots of markers, it is recommended to, instead of putting all the antibodies in the first antibody mix, to run a core panel. Main lineage markers can be included in this core panel, and in our case, our core panel had 15 markers, and we did not add the intracellular ones. Running a core panel will help you validate your panel, and after, when all the antibodies are added, if issues arise, it will be easier for you to track them and to know where they are coming from, as you will have already validated the core panel and you will know that the markers in the core panel are working well. After taking into account all these tricks and following all the steps that Kate has been talking about, we wanted to make sure that our gating strategy was also looking good and that we could clearly define and separate all the cell types that we were interested in. At this point, we found that our gating strategy was looking very good, and that we were able to gauge and quantify at least 44 populations of the innate and adaptive immune response. When analyzing our data with high-dimensional algorithms, we decided to use Fluorochrome clustering tool and overlaying the cells of interest on it. On this image, we are comparing naive with the 3 helminth-infected gut time points. What we found was that there was a big increase of infiltration of immune cells at day 14. Note, for example, the increase of eosinophils compared to the other time points. Interestingly, when comparing the same time points in mesenteric lymph nodes, we couldn't find as many differences than in gut. We found this quite relevant because routinely mesenteric lymph nodes have been used as a mirror of the intestine, while in here we demonstrate the importance of being able to digest and analyze infected gut in single cell to obtain unique and more specific information of the infected guts. To conclude, after 14 iterations, we were able to optimize a protocol to be able to obtain single cells out from helminth-infected intestine. And we believe that this won't only be useful for helminth-infected guts, it will also be useful to understand more about other gut impairment conditions. Also, we were able to design a 23-color spectral flow cytometry panel that will allow us to identify different innate and adaptive immune cells. And lastly, our data could be successfully analyzed with high-dimensional data algorithms. To finish, I would like to thank all the authors of these 3 publications, as their contribution have made the work much better, and especially Dr. Johannes Meyer and Kylie Price for their guidance and support. I would like to thank all the funders that have contributed to make this work possible, and also I would like to thank Cytek and BioLegend to invite me to talk about the work I've been doing.